Hello and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 8, Circles, Angles, and Shapes, Lesson 6, Sandcastles. Starting with the Ready section, our directions here say find the exact value of the indicated lengths. So when they say exact value, that means we do not want any decimal approximations. They want exact values. And we're also told that the triangles in problems 1, 2, and 3 are right triangles. First assigned question was number 2. And because we're told that it's a right triangle, we know that this angle in the bottom right has to be our right angle. So go ahead and put a box there. So what we have is we have a right triangle where we know two sides, and we are looking for the third side. Well, hopefully we know that in this situation, we can use the Pythagorean theorem to solve for our missing side. Now, the Pythagorean theorem, many of us know that as a squared plus b squared equals c squared, and that is true. What the Pythagorean theorem says is that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. So that gives us our sort of famous equation, a squared plus b squared equals c squared. The thing to keep in mind is that in this equation, your hypotenuse must always be c. If you're solving for the hypotenuse, or if you know the hypotenuse, it doesn't matter. C has to be across from the right angle. So looking at our picture here, that tells us that C has to be 50. You're kind of locked into that. Now A and B are interchangeable. They're the two legs. Well, one of them we know is 20. The other one we don't know. We're going to solve for it. We may as well just continue to use B. We can use really any letter that we want there. So now we want to get B by itself. So in order to get B by itself, well, first we'll simplify these squareds. So 20 squared is 400. B squared, there's nothing we can do with that at the moment. And 50 squared is 2,500. All right. Now I want to get B by itself. So the first thing I have to do is I have to get rid of this 400. So that cancels. And on the left, I'll go ahead and put this in the spare space over here. So on the left-hand side of the equal sign, we're left with just b squared. And then on the right, we have 2,500 minus 400, giving us 2,100 or 2,100. Now, to get b by itself, I now need to take the square root. So we're going to take the square root. So I end up getting, on the left, I end up getting b. Now, sometimes in algebra, when you take the square root like this, you need to include a plus minus. And the reason being, we're not sure whether b is positive or negative, because when you square it, you get a positive no matter what. So to account for that, sometimes you need to use a plus minus in this situation. However, in this particular problem, we don't need to use a plus minus because we're talking about the lengths of a triangle, and so we're not going to deal with negative length. So in this situation, we actually do not need our plus minus, which means we've still got the square root of 2,100. Now, I want to try to simplify this square root. And the way that we simplify square roots is we say, all right, I want to take my number here, which in this case is 2,100, and I want to try to break it up into the product of two numbers. Okay? So I want to multiply two numbers. I want to get 2,100. And specifically, I want my first number to be the largest square number that goes in evenly into 2,100. And as a reminder, my square numbers are 1, 4, 9, 16, 25, 36, and so on, right? Because we have 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. So these are the square numbers. And it turns out that in this situation, 100 is a square number because it's 10 squared. And 100 goes in evenly into this number. If you don't see that, any number that ends in two zeros is divisible by 100, just like any number that's divisible by 10 is going to have a single zero. So because there's two zeros at the end, we quote unquote know that 100 is going to go evenly into this number. It actually turns out it's also the largest square number that goes in evenly into 2100. Notice that there's other square numbers that go in. 4 would go in evenly, 25 would go in evenly, but 100 is the largest square number. And then the other factor that gives me 2100 here is, well, 21. So I've broken up 2100 into both 100 and 21. And the reason why I want to do this is because I can break this up into two square roots, just like this. The big square root becomes two smaller square roots. And the square root of 100, well, if you take a look over here, the square root of 100 is simply 10. So this becomes 10. And then the root 21, there's not really anything we can do with that because there's no square number other than 1. I don't really care about 1. There's no square number larger than 1 that divides evenly into 21. And so the square root of 21 is sort of trapped underneath the square root. There's not really anything that we can do about that. So what that means is our final answer here is 10 root 21. And again, we found that by applying the Pythagorean theorem and simplifying the equation, and then we had to simplify our square root using the method that was just described. Okay, question 3. So the directions again told us that this is a right triangle. So that has to be my right angle in the bottom left there. And again, we have a situation where we have a right triangle and we know two sides and we want to solve for the third side. And we've seen that we can apply the Pythagorean theorem. Now, I'm going to do this question kind of like the long way, and then I will show you a shortcut at the end. If you already know the shortcut, then that's great. Hold on to that. If you don't know the shortcut, you can always fall back on applying the Pythagorean theorem. And again, that's going to end up being the long way. And at the very end, we'll go through a kind of a shortcut in case you don't already know it. So again, the Pythagorean theorem says that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. Now in this situation, we actually don't know the hypotenuse. We're solving for that. So that means that our legs are both 16. So both A and B are 16. And we're solving for C. We may as well leave C there. Now, if you wanted to, you could evaluate 16 squared and get 256, and then double that and get 512, and sort of do all the algebra, if you will. However, it's going to make our job a little bit easier if notice that we have something squared plus that same thing squared. Well, that's actually the same thing as simply 2 times 16 squared equals c squared. Right? I have 2 of them. And again, it turns out, I'll do this in red, it turns out that this is 512. All right? But it also turns out that we don't need that. And in fact, if we go this route, it actually makes our job harder because what's going to happen now is we're going to take the square root of both sides to get c by itself. I'm also going to flip it so that the c is going to come over to the left. So what we end up getting is we end up getting c equals, we do not need a plus minus here because we're talking about the lengths of a triangle, and the lengths of a triangle are strictly positive, so we don't need a plus minus. So we end up getting c is the square root of, well, if I rearrange my order here and I put the 16 squared first times 2, just like that, well, notice what's going to happen here. When I break up this square root, I get the square root of 16 squared times the square root of 2, just like we did with question 3. But notice that I have the square root of 16 squared. Well, those are going to cancel, and I'm left with just 16. And then I get root 2. And that actually is our final answer, 16 root 2. Now, again, if we go back to this step here, and if you had plugged in for 16 squared and done that twice and added them, you would have gotten 512. And then 512 you'd have to rewrite as 256 times 2, which all gives us the same answer of 16 root 2. I just think it's easier to go this way because you end up just avoiding a lot of sort of doing and undoing, and the process, I think, is a little bit straightforward. However, if this process does not make sense to you, you can always evaluate everything and simplify the square root just like we did with question 2. I just think that this method's a little bit easier. Now, before we move on to the next question, notice that we've got some patterns here. So we have our final answer is 16 root 2. So I'll go ahead and write that over here, 16 root 2. Notice that our legs of this right triangle were themselves 16. Now, because the legs are congruent to each other, it means that this is a triangle that has two congruent sides, which means it is isosceles. So an isosceles triangle has two congruent sides. And in an isosceles right triangle, which I'll draw here, and I'll say simply x and x, in an isosceles right triangle, the hypotenuse is going to be x root 2 every single time. So if you didn't already know that, that's a very handy shortcut. So you don't have to use the Pythagorean theorem. You don't have to do all the calculations. In an isosceles right triangle, this relationship will always work. So because our original triangle had legs of 16, it means that the hypotenuse had to be 16 root 2. Because that's the way that the math works out. So both a long way of doing this problem and a short way, no matter how you do it, you should get 16 root 2 as your final answer. Question 4. So with question 4, we have I guess a big triangle. So the triangle on the outside, and that triangle is an equilateral triangle because all three sides are 28. So we got 28, 28, 28. So the big triangle is equilateral because all three sides are the same. But what we're looking for is this height. So this height going from the vertex down to the opposite side. And so we're looking for the height. We know it's a height because it forms a right triangle. Well, when you have a construction like this, when you have an equilateral triangle that has an altitude drawn from one vertex to the opposite side, it actually cuts the other side in half. So what's going to happen is this 28 on the bottom, because I have an altitude and it's in an equilateral triangle, what it does is it actually cuts that up into 14 and 14. Which, like, visually certainly makes sense. It looks like it cuts it in half, but it actually turns out that we can assume in this situation that the altitude cuts the triangle directly in half, which means each piece there is going to be 14. Now, if you notice, I'll look at the one on the right here, I suppose. If I don't want, just leave that like that. Okay. If I look on the right here. What we now have is we have a right triangle where we know two sides, and we are solving for the third side. So again, there's also a shortcut here for question 4, but if you don't see the shortcut and you want to use the Pythagorean theorem, once again, the Pythagorean theorem says that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. Now, looking at the triangle in red, we know our hypotenuse is 28. We also know that one of the legs is 14. We don't know the other leg. I'll continue to use B in this case. So 14 squared is 196. b squared is going to stay just where it is. 28 squared is 784. If we subtract 196 from both sides, I'll continue over here on the right, we end up getting b squared equals 784 minus 186 is 588. I need to take the square root of both sides to get b by itself, so I end up getting b equals. We do not need a plus minus here because we're just dealing with length, and length is always positive. So I have the square root of 588. And to simplify the square root of 588, what I want to do is I want to figure out, all right, what is the largest square number that goes in evenly into 588? And this may take some time on the calculator because a lot of stuff goes into 588. 588 divided by 4, that does not work. It's 588, sorry. So 588 divided by 4. Okay, that does work, but 4 is an extremely small square number. We should definitely continue to check other ones. So 588 divided by 9, that doesn't work. 588 divided by 16, that doesn't work. 588 divided by 25 is not going to work because this number does not end in 5. 588 divided by 36 is not going to work because 3 did not work earlier. 588 divided by 49. So this does work, right? So currently 49 is our largest square number, but we should also continue, should keep going. 64 is not going to work. I already know 81 is not going to work. I know 100 is not going to work. 121 is not going to work. 144 is not going to work. 169 is not going to work. However, 588 divided by 14 squared, which is 196, does in fact work. So with this question, the largest square number that goes in evenly into 588 is 196, and 196 is 14 squared, rather. Okay? So 196 is our square number that we want in this situation. So this becomes 196 times 3. And the reason why we want to do this is because we can split this up into two smaller square roots. The big square root gets broken up. And as we just said, the square root of 196 is 14. So we end up getting 14 root 3. Root 3, like that. Okay, I'll just redo that. So our final answer here is 14 root 3. And if I go back to my original picture here, notice that the triangle in red here, well, the original triangle was an equilateral triangle, which means that this angle measurement is 60 degrees because it's 60, 60, 60 at each vertex. Well, if this is 90, it means that this angle is going to be 30 because it has to sum to 180, plus my angle at the top there gets cut in half, so it becomes 30 and 30. So what that gives us is that gives us a 30, 60, 90 triangle, and in a 30, 60, 90 triangle, which I'll just draw over here. So if you have a 30, 60, 90 triangle like we do here, well, if the small leg is x, it turns out that the longer leg is x root 3, and that my hypotenuse is 2x. So notice in this situation, my x was 14. The hypotenuse is double that, which is 28, and my longer leg is the same 14, but now with a root 3, which is the answer that we got. So again, with question 4, there's nothing wrong with using the Pythagorean theorem here and sort of doing all of the math and the algebra and things like that. However, you can hopefully see that if you can recognize the pattern that exists in a 30, 60, 90 triangle, it cuts out a lot of the work that you have to do in this problem. And you can simply say, well, it's the longer leg is going to be the shorter leg times root 3. So it's simply 14 root 3. And that is our final answer for number 4. Moving on to the set section. Question number 6, the directions say this. In 1946, a miracle cleaning product was launched in the United States. It was granular laundry detergent instead of bar soap. For almost 20 years after 1946, laundry detergent came in a box shaped much like a box of cereal. In the late 1960s, the shape of the box changed so that it would fit better on a shelf. No one wanted to buy the new detergent because it was the same price, but the box looked much smaller. Prove to consumers that the new box was actually a better bargain. So these kind of like real world situations were always kind of interesting to me about, people's, maybe they're a little confused about geometry and they end up making financial decisions that aren't actually based, the numbers don't really check out. So here are our two boxes. The box on the left, which was launched like right after World War II, kind of shaped like a cereal box, and then in the 60s it changed to a more cube-looking box. It's not actually a cube, but it's closer to a cube than the one on the left. So we want to prove that the new box, the box on the right, is the better bargain if these two things are the same price. Now, what consumers care about in this context is they care about how much detergent is in the box, right? They don't care about they don't care about surface area, right? Surface area is the area on the outside of the box. Why would anyone care about that, right? What they care about is the amount of detergent that's inside the box. That means we're talking about volume. So we want to compare the volume of these two boxes. Now, both of these boxes, in a geometric sense, are rectangular prisms. So they're both rectangular prisms. And in order to find the volume of any prism or cylinder, the way that you can find the volume of any prism or cylinder is to find the area of the base and then multiply by the height of the figure. So in the first case, our base is this rectangle at the bottom, and we can see that the dimensions of that rectangle, well, one of the dimensions is 10, and then the other dimension is actually given up here at the top, which is 3. So I'll just move that down there at the bottom. So the base is a 10 by 3 rectangle. So if I want the area of a rectangle, I simply multiply by my two dimensions, so 10 times 3. That's the area of my base, and then the height of the figure is how far apart are the bases. Well, they give us that. They give us 14. So it's simply 14. So my volume here is going to be 10 times 3 times 14, which is 420 cubic inches of detergent. So the box on the left, the cereal box, contains 420 cubic inches of detergent. Now, before we go on to the one on the right, notice that realistically, because multiplication is commutative, the order does not matter here. So even though we did 10 times 3 times 14, you can probably see that you can multiply these three numbers in really any order. You could do 14 times 3 times 10. You could do 10 times 14 times 3. The order doesn't really matter. So if you did this in a different order but still got 420, that's actually perfectly fine. I like to do it in this way because we can always fall back on the fact that for any prism or cylinder, it's the area of the base times the height. And that sort of general formula does not change between different kinds of prisms or cylinders. So we'll call this V sub A. Now, to get the second volume, which we'll call V sub B, this is again a rectangular prism. And now our base is this rectangle here at the bottom. One of the dimensions is 9. The other dimension they give us up here is 6, so I'll put a 6 right there. So if I want the area of the base, my base is a rectangle that has dimensions of 9 and 6. So the area of the base is going to be 9 times 6. And then I want to multiply by the height of the figure, which is the distance between the bases, which in this case is 8. So I'm going to take that 9 times 6, which is 54, and multiply by 8. So I get 9 times 6 times 8, and 9 times 6 times 8 is 432 cubic inches of detergent. They're cubic inches because volume is a three-dimensional unit of measurement. So volume is always cubic units, and we're talking about inches, so it's 432 cubic inches. So I don't think that we have to add any words here. I think that it's sufficient to see that 432 is larger than 420, and so therefore I think that this is sufficient evidence that the box on the right, despite looking smaller, actually does contain more detergent, assuming that the box is filled, which I think we have to kind of assume mathematically. But yeah, so the more cube-looking box on the right actually does contain more detergent than the cereal box thing on the left here. Next assigned question was number 8. Question 8 says, a distribution company uses a small packing container as shown in the figure. Find the volume. So we have a packing container with a bunch of dimensions here. This is a rectangular prism, and we want to find the volume. And in order to find the volume of any prism or cylinder, it's going to be the area of the base times the height. This is a rectangular prism. That means that our base is a rectangle. So it makes it a rectangular prism. The dimensions of that rectangle are 15 and 6. So if I want the area of my base, it is going to be 15 times 6, which is 90, by the way. So the area is 90 square centimeters. And then in order to get the volume, I multiply by the height, which is the distance between the bases, which is 16. So I can take this and multiply by 16. And I simplify this, and I end up getting 1,440. Now we're talking about centimeters here, and it's volume, so it's cubic centimeters. And that is my answer, 1440 cubic centimeters. And again, notice that the order doesn't really matter here. As long as you multiply these three numbers in really any order, you will get 1,440. I just like to think of it as the area of the base times the height. Question 9 says, a large order is placed with the distribution company in problem 8 for a container that has a capacity of 38,500 cubic centimeters. The company has a similar container that is larger than the one in problem 8 by a scale factor of 3. That's important. Will the larger container be enough to contain 38,500 cubic centimeters? Justify your answer. Now, there's at least two different ways to do this problem. There's a way, I don't think it's a long way, but it's a longer way and then a shorter way. So we'll do the longer way first. The longer way to do this problem is to basically just redo question 8, except take all of our dimensions here, the length, width, and height, and multiply them all by 3, and then just find the volume of the new box that results from that. So the old box, the smaller box, had a base that was a rectangle that had dimensions that were 15 and 6. So if I want the volume of the bigger box, I can simply take each of those and multiply by 3. That'll give me the new area of my base. So we'll say that the volume is, now there's the area of the base. Now the area of the base, like we said, it's going to be 15, but that 15 is now 3 times as large. Okay, so now it's 15 times 3. Then I'm going to take my 6, and I'm also going to multiply that by 3. So what we have so far is we have the area of the new base, because the 15 we multiplied by 3, the 6 we multiplied by 3, and when we multiply those together, we get the area of the new base. To get the volume, I want to multiply by the height. Well, the height of the original one was 16, so I'm going to also multiply that by 3. So we get 16 times 3. Now, if I plug this in, I should get my total area, which it actually turns out is 38,880 cubic centimeters. So 15 times 3 was the new length, 6 times 3 was the new width, 6 times 3 was the new width, 16 times 3 was the new height. If I multiply all three of those together, I get 38,880. Now, 38,880 is larger than 38,500. And so, will the larger container be big enough? Yes. Right? So our final answer here is that yes, the larger container, because it has a volume of 38,880, will be able to contain 38,500, barely, but it does in fact work. Now, before we close out this problem, I do just want to mention another way to do question 9 that, in my opinion, is slightly easier than the one that we just did, but maybe you'll disagree, I'm not sure. Notice that with question 8, we found the volume of the smaller box, right? Our answer for question 8 was 1,440. If I take that answer of 1,440, which is the volume of the smaller box, and if I multiply by something, I will get my final answer, which turned out to be 38,880. Now, notice that because the scale factor was 3, we multiplied each dimension by 3. We multiplied the length by 3, we multiplied the width by 3, and we multiplied the height by 3. So that's all fine when you're talking about linear distance, because length or distance is one dimension. Volume is a three-dimensional unit of measurement. What that means is if we're going to take the smaller box and multiply by our scale factor, it is not sufficient to simply multiply by 3. So you cannot take your old volume, multiply by your scale factor, and get the new volume. It just doesn't work that way, because volume is 3 dimensions, not 1 dimension. So in order to do it this way, we don't multiply by 3, but we multiply by 3 cubed. And that 3, the exponent, is because volume is always a 3-dimensional unit of measurement. Also, if you take a look at our original equation, notice that we're multiplying by not 1, not 2, but 3 threes. So that's where your 3 cubed comes from, because every single dimension got multiplied by 3. So you have to do it 3 times. So 3 times 3 times 3, which of course is 3 cubed. If you go ahead and simplify this, you will get the same exact 38,880 that we already got by doing it the other method. So, in my opinion, I actually think that this method of using our scale factor and using our volume of that we got for question 8, I actually think that this is preferred, and I would say try to use this method if you can. However, you can fall back on the first way that we solved this problem because obviously both of them result in the same answer of 38,880 cubic centimeters. And so therefore, yes, the larger container, no matter how you solve it, will be big enough. As always, we'll wrap up this assignment in the Go section. And the first set of directions here say, change the measure of the given angle to radian measure. Leave pi in your answers. Okay. First assigned question is number 12. Number 12 asks us to convert 270 degrees into radians. The way that we're going to do this is we are going to start with our given angle measurement, which in this case is 270 degrees. And I actually would encourage you, if you're not someone who's always very specific about including the degree symbol in this kind of situation, in this kind of problem, I would strongly encourage you to include the degree symbol because it's going to help you keep track of, are we talking about degrees or are we talking about radians? In this problem, if a number has a degree symbol, then you can assume it's degrees. And if it does not have a degree symbol, you kind of have to assume that you're talking about radians. So we're just rewriting the 270, and we really want to include the degree symbol. Now, what we're going to do is we're going to take this 270, and we're going to multiply by the number 1. And the reason why we're going to multiply by the number 1 is when you multiply by the number 1, you don't change it. Right? 7 times 1 is 7. Negative 4 times 1 is negative 4. So you don't actually change it by multiplying by 1. However, we're going to write the number 1 in kind of a weird way. We're going to write it, first of all, it's going to be a fraction. Now, we know that anything over itself is 1, other than 0. Any non-zero value over itself is 1. And we're going to utilize the conversion factor of 180 degrees equaling pi radians. So we're going to use this fact to express the number 1 as pi radians over 180 degrees. I'm going to pause here because I really want to make sure that people understand this. What we're doing is we're taking the 270 degrees and we're multiplying by 1, and anything over itself is 1, and we just said that 180 degrees is the same thing as pi radians. So this fraction here where I have pi radians over 180 degrees, this actually does equal, this whole thing here equals the number 1 because it's something over itself, because those two things are the same thing. Pi radians is 180 degrees. Now, the reason why I wrote my fraction like this, with radians in the numerator and degrees in the denominator, is what's going to happen is I have degrees in essentially the numerator and the denominator, so my degrees are going to go away, which is what I want. I don't want to be in degrees anymore. I want to be in radians. So by including the 180 in the denominator, I have successfully canceled out my degrees, which leaves me with 270 pi in my numerator over 180 in my denominator. So this 270 gets smushed up into the numerator where the pi is, and I end up getting 270 over 180. So now in order to finish out this problem, all I need to do is I need to simplify 270 over 180. Well, if you have a calculator, this is super easy, a graphing calculator. If you have a graphing calculator, you can type in You can ignore the pi temporarily, and you can just say 270 divided by 180, then hit math, enter, enter, and you'll get your final fraction. But assuming that you do not have access to a graphing calculator and you have to do this, quote unquote, by hand, well, first of all, they both end in a 0, so those go away. So right off the bat, this simplifies to 27 pi over 18, which is better, right? We're making progress. Now, between the 27 and the 18, we want to identify the GCF and factor it out and cancel it. So the GCF of 27 and 18 is 9. So if we divide out a 9 from both the numerator and the denominator, 27 divided by 9 is 3. We still have the pi there. We haven't really done anything with it. And then 18 divided by 9 is 2. And that is our final simplified answer here. If we go back to the original fraction of 270 over 180, the GCF there would have been 90. But we sort of did it in two parts. We did the 10, then the 9. But if you wanted to do it in one step, you could just divide out a 90 from both terms, and that would still give you the same answer of 3 pi over 2 radians. And that is our final answer for number 12. Question 13 asks us to convert 210 degrees into radians. Just like in the last problem, we're going to start with our degree measurement, our angle measured in degrees. We're going to multiply by the number 1. And the version of the number 1 that we're going to multiply by is we want to get rid of degrees. And so the degrees are going to go in the denominator of this fraction because I want them to cancel. And we saw that our conversion factor that we're always going to go back to is that 180 degrees is the same thing as pi radians. So that is, in fact, the number 1, which means we're not really changing anything. We're just changing our units, but we're not changing the magnitude or the quantity in any way. So our degrees cancel, which is nice, that's what we want to happen. So we end up getting 210 pi over 180. And notice that I no longer have degrees here because my degrees canceled. So this is our answer, and now all we need to do is simplify it. Right off the bat, I see that they both end in 0, so I can actually just drop a 0 immediately. That way I'm dealing with slightly smaller numbers. So I've got 21 pi over 18. We're going to temporarily ignore the pi, and we're just going to focus on just the 21 and the 18. If you do 21 divided by 18, math, enter, enter, it'll simplify the fraction for you. If you do not have a calculator or you're not allowed to use a calculator or whatever the context may be, you want to find the GCF of 21 and 18, and that'll cancel out. The GCF of 21 and 18 is 3. So 21 divided by 3 is 7. And we have to include the pi. We're not really evaluating it, but it's definitely still there. And then 18 divided by 3 is 6. And so this fraction reduces to 7 pi over 6, and that is our radian measure for the angle 210 degrees, is the same thing as 7 pi over 6 radians. Question 14. 14 asks us to convert 300 degrees into radians. It's going to be very similar to the last two problems. So we're going to start with 300 degrees. We're going to multiply by the number 1 expressed as a fraction of something over itself. We want to get rid of degrees, so degrees are going to go in our denominator, and we know that 180 degrees is the same thing as pi radians. My degrees go away, which is great. That's what I want to happen. So the 300 gets smushed up into the numerator, so this becomes 300 pi over 180. I think it's worth it to just drop a 0 from each. You're essentially dividing by 10. That way you're just dealing with smaller numbers. On the graphing calculator, 30 divided by 18, math enter enter, that'll simplify it for you. If we're going to do this by hand, we need to find the GCF of 30 and 18, and the GCF of 30 and 18 is 6. So 30 divided by 6 is 5. We can't forget our pi. And then 18 divided by 6 is 3. That fraction is fully simplified, and so 300 degrees is, if you express that in radians, you get 5 pi over 3. So those two angles are identical angles, they're just measured in two different things, degrees versus radians. Now, the next set of directions say, change the measure of the given angle to degrees. So identical directions to, well, not, I guess not identical, but very similar directions as the first section here. We're just, instead of going from degrees to radians, we're now going backwards. So we're going from radians into degrees. Our general process is actually not going to change in that we're going to start with our angle measurement. So we're starting with oh, 3. Why is this not? Come on, man. 3. There we go. 3 pi over 4. So we're going to start with 3 pi over 4 radians. And now we're going to multiply again by the number 1. And that number 1 is going to be expressed as a fraction of something over itself. Now the difference with the first section is that even though we're again going to multiply by the number 1, and again we're going to use our conversion factor, this time we're going to use the reciprocal of the fraction that we used in the first half of the go section here. So in the first half of the go section, our fraction was right here. It was pi over 180 degrees. This time, I'm going to flip it, and I'm going to say, all right, well, I'm actually going to put radians in the denominator because I want those to go away. I don't want to be in radians anymore. I want to be in degrees. And in the numerator, I'm going to introduce degrees. Right? So notice that for the first time, I'm including a degree symbol here, and that degree symbol is not going to get canceled out and certainly not going to be in the denominator. So I'm writing my fraction like this because I want to get rid of radians and I want to introduce degrees. And so that's why I wrote the fraction the way that I wrote it. Notice that I have a pi in both the numerator and the denominator. So that goes away, which makes our job significantly easier. And we're left with just, in the numerator, 3 times 180. My denominator is 4, and this whole thing is expressed in degrees. You can easily type this into a calculator. If you want to do it by hand, 180 divided by 4 is 45, and 45 times 3 is 135. But again, if you have access to a calculator, feel free to use it. And again, we're talking about degrees, so I don't want to forget my degree symbol. That's the whole reason why we're doing this. And that is my final answer. So 3 pi over 4 radians is the same thing. It's the same angle as 135 degrees. They're just two different ways of measuring the same thing. (19) 19 asks us to convert 2 pi over 5 radians into degrees. For anyone, I don't think anyone is familiar with the unit circle, but if anyone is familiar with the unit circle, this radian measure may look a little strange because it doesn't really pop up on the unit circle, but I'm not sure if anyone's been exposed to that yet. But let's just go ahead and convert this. So we've got 2 pi over 5. That's my original radian measure of my angle. I'm going to multiply by the number 1, which I'm allowed to do. When you multiply by 1, you don't really change anything. You don't change the quantity in any meaningful way. And the version of the number 1 that I'm going to multiply by is my conversion factor between radians and degrees. And I want to put radians in the denominator because I want to get rid of them. And I want to put degrees in the numerator because I want to introduce them. So I'm going to write my fraction as 180 degrees over pi. And because those are the same thing, I'm multiplying by 1, because anything over itself is 1. My pi's go away, which is nice. And I am left with 2 times 180 over 5, and we are now talking about degrees. So again, you can type this in if you want. If you do this by hand, 2 times 180 is 360, and 1/5 of 360 is 72. But you can also just type that in if you want. And so 2 pi over 5 radians is equivalent to 72 degrees when you're talking about angle measurements. Finally, question 21. Now, 21 might look a little bit different because the last couple problems that we did were fractions involving pi, and now we have a decimal that does not involve pi. But our general approach is actually not going to change. We're going to start with our radian measure. Now, there's no degree symbol here, so this is not 4.71 degrees. If this was degrees, you would need a degree symbol. So even though there's no pi, the lack of a degree symbol tells us that this is radians. Not all radian measures are expressed in terms of pi. This one, essentially pi has been plugged in. You know, maybe they used, I don't know, 3.14, and they plugged it in and they got 4.71. So we're going to start with our radian measure, and just like always, we're going to multiply by the number 1. We want to get rid of radians. We want to introduce degrees, just like this. And so what we end up getting is 180 times 4.71 over pi, and this whole thing is degrees. All right, well, that's our answer, but it's certainly a kind of an ugly-looking answer. And honestly, even if we did 180 times 4.71, you're still going to get a decimal inside of a fraction. So it's probably for the best that we just evaluate this and just see what we get. So this I certainly can't do in my head, so we go to our calculator, and we are going to type in 4.71 times 180 and divided by pi. We don't need any parentheses here. If you want to include parentheses, you're more than welcome to, but it turns out that they're actually not necessary in this problem. But if using parentheses in some way would make you more comfortable, that's fine. Just don't use them in a way that's going to give you the wrong answer. So the final answer here is 269.86. And for reasons that I'll explain in just a second, it didn't say what to round to. And normally by default, I tend to round to 2 decimal places. But on this specific problem, and again, you'll see why in just a second, I'm actually going to round to the nearest whole number. So the nearest whole number here is 270. So that's actually the answer that I'm going to give here, because the directions did not say how to round. So I can actually just kind of choose however I want to round. So I'm going to round to the nearest whole number. So this is approximately, 270 degrees. That's our answer. And before we go, if I go all the way back up to question 12, notice that, I had erased some stuff here, but this was our final answer right here. So notice that for question 12, our original question was 270 degrees, and our final answer was 3 pi over 2. And if I go back to my calculator here and I actually evaluate 3 pi over 2, so 3 pi over 2, I get 4.71, and then some change, but I get 4.71, which is the value that we started with, 4.71. So The reason why we rounded to the nearest whole number here is because clearly with question 21, they did 3 pi over 2 and evaluated it and got 4.71, and 3 pi over 2 is exactly 270 degrees. So I think it's reasonable to approximate this to the nearest whole number because that's clearly what this question was trying to do. And so for question 21, that's 270 degrees, and that's our final answer.